For the following functions, we're supposed to state if it is a polynomial. If yes, state the degree, in behavior, rises or falls on the left and the right, and possible number of x-intercepts and possible number of turning points. So for problem A, if you'll notice, this will actually simplify. If you did simplify that, notice right here, the 2x to the third over the x to the fifth would simplify into 2 over x squared. That makes this not a polynomial. How did I come up with the x squared? I'm subtracting 5 minus 3, and the square stays on the bottom, or in the denominator, because the denominator exponent is bigger than the numerator exponent. Of course, there is more to this function, but I'm not going to even simplify it past that, because any time the x exponent in the denominator is larger than the numerator, you do not have a polynomial. You need whole number, non-negative, no x's in the denominator, no radicals. So this is not a polynomial, so I'm not going to answer the rest of the questions about it. When you look at the second problem, you have a polynomial. Notice it's x to the third, x squared, x to the first, a constant. It's even in descending powers order. All of the exponents, so what I'm talking about, all of these guys, ooh, I didn't mean to scribble it out. Hold on, let me erase that. I was trying to use a highlighter. Let me try that again. So all of these guys right here, that's a 1 right there, are whole numbers. And so you always want your x or your variable exponents to be whole numbers. Including 0. There's really an x to the 0 down here at the end. You could put an x to the 0 right there. I need a pen to do that. Let me do that for you. Okay, but notice all those exponents are whole numbers. No negatives, no fractions, or anything like that. So this is a polynomial. So if I keep going, I'm supposed to state the degree. The degree is the highest exponent, so this guy is a degree 3. The end behavior, whether it rises or falls on the left and the right. Notice anytime your degree is an odd number, it does the opposite thing. And on the left, it's going to fall, and it falls to negative infinity, or you could just say it falls, and on the right, it rises. And that's just what you need to memorize. Again, because it's odd, it's an odd degree, they go in opposite directions. One falls and one rises. When you have a positive leading coefficient, so what I'm talking about is the number in front of your coefficient in front of your x to the highest power, anytime that's positive, and in this case it's positive 1, then it's going to fall on the left and rise on the right. The possible number of x-intercepts in this situation is 3. So we have up to 3 x-intercepts. We don't know exactly how many we have until we find the zeros or the x-intercepts, but we know we can't have any more than 3, whatever the degree is. The number of turning points, and y'all, what turning points are is when you graph it, there's a turning point and there's a turning point. It's a max and min values, and you can have up to the degree minus 1. So in this case, up to 3 minus 1, or 2 turning points. You might have 2, you might have 1, you might not have any, but it can't be any more than the degree minus 1. Okay, let's try another one. Next problem. We are looking at p of x equals negative 5x to the fifth minus 6x to the fourth plus 2x minus 3. Notice the degree is 5, and it is a polynomial. I don't have any negative exponents. I don't have any fraction exponents. I don't have any denominators. I don't have any radicals like square roots, cube roots. So this is definitely a polynomial. Okay, it is a degree 5 because the highest exponent of your variable is 5, which means it has up to 5 x-intercepts, right? And up to 4 turning points. The x-intercepts is always as high as the degree, and the number of turning points is always as high as the degree minus 1. How about end behavior? Because the degree is an odd number, that means it goes in opposite directions, but because you have a negative leading coefficient this time, a negative 5, that means you're going to go left is going to be rising, which is opposite of the last problem, and on the right, the graph will be falling. And again, that's just what information you have to memorize, the 4 cases. Next problem. Okay, now we have a negative 5x to the 2/3 minus 7x plus 4. Y'all, this guy is not a polynomial, right? Because you can't have a fractional exponent. That is the same as a radical, actually. And so all I have to put on this problem is it's not a polynomial, and I don't have to answer any of those other questions. Now, that's not to say it doesn't have end behavior, it doesn't have x-intercepts, it doesn't have turning points, but we don't know how to answer those questions about a problem that's not a polynomial. This entire chapter, or at least this section, focuses on polynomials. So that's all we have to do for this problem. Next problem, we're looking at f of x equals 11 square root of x. Well, folks, once again, we do not have a polynomial. Why not? Because anytime you have a radical, and what I mean by a radical is anything with that symbol in it. It could be a square root, like in this case. It could be a cube root. It could be a 4th root. It could be a 5th root. Any of that means it is not a polynomial, and therefore we will not answer all those questions about the problem. Example F. Example F. We've got 3x to the 6th plus 2x to the 3rd minus 1. This guy is a polynomial because we have nice whole exponents with our variable. So that means we can answer all of these questions. So let's do that. So what is the degree of this thing? This is a degree 6, okay, which means it has up to 6 x-intercepts, and it has up to 5 turning points. So you always take the degree and minus 1 for the turning points, and the degree, the same as the degree for the x-intercepts. But that doesn't mean it has 6 x-intercepts. It could have up to 6, okay? It could have 5 or 4 or 3 or 2 or 1 or even 0 x-intercepts, but it definitely doesn't have 7 or any more than that. Same thing with turning points. It could have 5 turning points, but it might have 4 or 3 or 2 or 1 or no turning points, but it's not going to have 6 turning points. That's impossible. Now, in behavior, because you have an even degree, that means they point in the same direction. And because you have a positive 3 leading coefficient, it's the positive part, means they both point upward. Or you could say on the left, I always try to do the left first, like reading a book. On the left, you're rising. And if they point in the same direction, on the right, you're rising also. And again, that's in behavior, just memorize. It's also called the leading coefficient test. More of these? Yes, we have more of these. Now check this problem out. This problem is not factored. So that makes answering these questions not as quick, but it is a polynomial. If I were to multiply this out, and let's don't, because it would be a lot of work, I would first need to multiply x minus 1 times x minus 1 to handle that square. Take that trinomial you get from there and then maybe multiply it times x plus 2. And then take that term, that polynomial, not term, I'm sorry, polynomial with a lot of terms, and multiply it times x minus 3. And then take that even bigger polynomial and distribute the 4 inside. We don't want to do that. Okay, what I'm imagining is if I did do all that, we would definitely have a polynomial because we don't have any denominator. We don't have any square roots, cube roots, in other words, no radicals. We don't have any fractional exponents. So I know I definitely have a polynomial. Okay, got that. Now, what about the degree? The degree is not 2 because of this x squared out here. We would have to imagine if we were to multiply this out, it would end up being a negative 4 from here. Now, times the x, because that's the highest here, times x to the 1st, that's the highest here, times this is going to be an x squared here. And then you're going to have a whole bunch of other terms after that that we don't care about. So what I'm trying to say is this is a negative 4 x to the, remember you add these exponents. There's a 1 there, plus 2, that's 4. Negative x to the 4th plus a bunch of stuff. Now that means we have a degree 4. I'm not concerned about the other stuff. I just want to know what the leading coefficient is. It's negative 4. And what the degree is. It's 4. So that means we have up to 4 x-intercepts, okay, and up to 3 turning points. Oops, can't spell. Hold on. Turning points. What else do we need to know? The end behavior. Now, when you have a degree 4, that's even. Means they point in the same direction. But guess what? They both point downward this time because of the negative in front. So, as we go to the left, the graph is falling. In other words, pointing downward. If we go to the right, the graph is falling. Again, because of the negative leading coefficient. And they're both down. So, anytime you have an even number for the degree, 2, 4, 6, 8, 10, they point in the same direction. If your coefficient, your leading coefficient's negative, both odds are falling. If in like the last problem, like this guy, the leading coefficient was positive, positive 3, both sides are rising. And just a quick review, remember when you have an odd degree, they point in opposite directions. And then your coefficient tells you if the left is down or the right is down, if the left is up or the right. I said that crazy, but you know what I mean. Okay? Now problem 2, I'm supposed to match the polynomial with the given graph. Or graphs. We have a lot of graphs. We have a lot of polynomials. I'm supposed to use the X-Intercepts, the end behavior, and multiplicity to help us match. Now, I'm going to just write a few notes right here on each problem. And then when we go to the graphs on the next slides, I'm going to write a few notes there. And then we're going to match. Okay, so things I need to know here. Here, guess what, y'all? That first problem is a degree 2. What are the ends doing? They're both pointing upward. The left is pointing upward and the right is pointing. How do I know that? Because it's an even degree with a positive leading coefficient. That means both are pointing upward. What about the x-intercepts? Well, you remember how to find x-intercepts? You set your function equal to 0. Now, if it's factored, it's real easy to see what the x-intercepts are. But this, y'all, this guy's not factored. I'm trying to find numbers that multiply to be 6 and add to be negative 5. That's a minus 2 and a minus 3 equals 0. Hey, that tells me what my x-intercepts are. If I set x minus 2 equal to 0, that gives me x equals 2. And if I set x minus 3 equal to 0, that gives me x equals 3. So I'm going to use the fact that these guys are both pointing upward and that my x-intercepts are 2 and 3. You could also use the fact that you can only have one turning point because the degree is 2 and you can only have one less than that turning point. That could help you out as well. These have multiplicity of 1, so the graph is going to cross through these x-intercepts. Let me switch colors on you and analyze the next one before we even do any matching. Now check this out. This is x to the first, x to the first, x to the first, and then x squared. So it's a degree 1, 2, 3, 4, 5. So this is a degree 5. What does that mean? They point in opposite directions. Okay? Now I have a negative leading coefficient, which means the left side is pointing upward and the right side is pointing downward. Okay? I also know I have x-intercepts of x equals 3, x equals negative 1, x equals negative 2, and x equals negative 5. Keep that in mind when we go match, okay? This is enough probably for you to match on your own right now. But I'm going to move on, and like I said, let's analyze every one of these, and then we'll look at the graph and then match. Now, look at this. Again, it's all factored out, which means finding zeros or x-intercepts. Remember, those are the same thing, but x-intercepts can only be real numbers, where zeros, it's possible they could be imaginary numbers also. But let's look at our degree. Okay, what is the degree? Well, when it's factored, you have to just imagine multiplying all this out. So x to the first times x to the first times x to the first times x to the first is going to give you x to the fourth. And the leading coefficient's negative. So that means both sides are pointing downward. The left is falling and the right is falling. What else do we know? We have x-intercepts of x equals 3. X equals negative 1, x equals negative 2, and x equals negative 5. Is it always the opposite of these binomial factors? Sure is, right? This negative in the front doesn't affect anything. As a matter of fact, when you set this equal to 0, you divide both sides by negative 1, and the negative is gone. It does affect the end behavior. When I say it doesn't affect anything, that's a lie. It doesn't affect the zeros, okay? Now, let me change colors again on you, and let's analyze the next one. So this is an x to the first times 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 x to the first. Notice there's 1, 2, 3, 4, 5 of these. This is a degree 5. The leading coefficient's positive. That's like a positive 1 right there. That means the left side is pointing upward and the right side is pointing downward. And what are my zeros? Hey, that gives me a 0. So x equals 0, x equals 2, x equals 1, x equals negative 2, and x equals negative 4. And then this last situation, what color have I not used? Let's use orange, okay? Now, again, with a degree, this is x to the first, x to the first. This is an x squared. So that's going to give me a degree 4 when I add all those exponents up. Now remember, the only time you add exponents to get a degree is if it's factored. If everything is multiplied out. Look, the first one, we didn't add exponents, right? We took the highest because that's all multiplied out. Now, our leading coefficient is negative. So if you have an even degree and a negative leading coefficient, that means they're both pointing downward. As a matter of fact, look, check your directions. We do have two graphs that are both pointing downward here, number 3 and number 5. But the x-intercepts are going to be the difference. Now here I have an x-intercept of 2. Here I have an x-intercept of negative 1. Here I have an x-intercept of 3. Now notice that's 5 polynomials that we need to match. Now I'm going to go to the next slide and look at the graphs and analyze the graphs, and then you could even match from there, but we'll finish it completely and do all the matching as well. So when I look at my graphs, here I go. Graph A right here, you could count the turning points. There's 1, 2, 3, 4, which means y'all this guy A has to be a degree 5 or higher. Look how many x-intercepts we have. 1, 2, 3, 4, 5. I have 5 x-intercepts. What does that mean? It's a degree 5 or higher. Has to be, because the degree is either the same as the x-intercept or more. Remember, I'm thinking about that backwards. Now, it might help just to write our x-intercepts down. So x-intercept, look, there's one right there. Uh-oh. I'm trying to change the graph and not write. So one right there, x equals negative 4 is an x-intercept. This guy right here is x equals negative 2 is an x-intercept. Right there is x equals 0. And then x equals 1. And then x equals 2. That's enough to match right there. But notice the end behavior, it's down on the left and up on the right. Okay, now let's keep going. Again, my colors now are not going to match what we have on the previous page. I'm not trying to do that. I'm just trying to make them different colors to discern what's going on. Here we got 2 x-intercepts. Look, there's one right there and there's one right there. What are those values? Let's look at the scale. So if that's a 5, then I'm counting by 1. That's a 2 and a 3. So x equals 2 and x equals 3. What else is going on? Hey, the left is pointing upward and the right is pointing upward. That's probably enough to match our graph, right? All right, let's look at the next graph and change colors. I have an x-intercept right here, but that guy's interesting. Look how it just bounced back the other way. So you know what? At x equals negative 5, we have even multiplicity. Whenever the graph just hits the x-axis and bounces back the other way, and that doesn't happen on either of these two. Look, it almost looks like it does here, but it does dip below. But here it literally touches and goes back the other way. That means we have even multiplicity. That means that x equals negative 5 showed up either 2 times, 4 times, 6 times, or 8 times. We also have an x-intercept right here. That was like x equals negative 2. And there's another one right there at x equals negative 1. And then there's even another one right there, 1, 2, 3. At x equals 3. Check out the end behavior. Notice that's going up on the left, and look, it's going down on the right. Now from there, I bet we could go back and match those. So let's look for the orange. Let's go to the previous page. Don't look for the color orange because it might not match that at all. I just mean these negative 4, negative 2, 0, 1, 2, all those x-intercepts, and then down on the left and up on the right. Let's see if we can find it. Okay, I'm looking for negative, look right here, negative 4, negative 2, 1, 2, 0, and then that's up on the left and down on the right. Y'all had to pause the video for a minute because I was like, oh no, I found it. Look, the intercepts match. Matter of fact, 4 is the only one with those intercepts, but my end behavior didn't match. Well, here's why. Because I did the end behavior wrong right here on this page. I did it too quickly. Look, an odd degree with a positive leading coefficient. I might have been looking at this one accidentally. So this is a positive leading coefficient. There we go. I'm trying to move stuff around again. I'm sorry. So with a positive leading coefficient right here, so this is positive. That's what I'm trying to do. Then this should have been down on the left and up on the right. And that's what I get for trying to do these two quickly. But this was A. For sure, that's A. The -4 X-intercept alone gives it away if you're trying to weed things out. Now let's look at graph B. Look, graph B has x equals 2 and x equals 3, and both sides are pointing up. And look, that's this one right here. X equals 2 and x equals 3, and both sides are pointing up. Everything else has got more zeros than that, or x-intercepts than that. So that one's real clear that number 1 matches to B. I'm trying to move all my work around. There's B, okay? And then let's see if we can match C. Now C, notice the left side's up and the right side's down. -5 has even multiplicity, so it shows up twice when we find our x-intercepts. We also have -2, -1, and 3. Let's see what we can do with that. Okay, look at there. I've even got it circled on number 2, -5, and I didn't write down it had multiplicity of 2, but it does because it's really x plus 5 twice. And then we're up on the left and down on the right. Let's go check again. I'm up on the left and down on the right. Yeah, that's C right there where you have x plus 5 squared. Okay, now I have more graphs to take a look at, so let me go to that slide. So there's going to be graphs D, E, and F. Notice everybody doesn't have a match. Now, D right here, notice what we got going on. Okay, so it's both ends are pointing upward, so we have an even degree. And I have zeros of x equals -1 and x is equal to, right here, our x-intercepts, and x equals 6. Okay, so let's go ahead and analyze the next one too, and then we'll go match. Okay, so on E, notice both sides are pointing down. So we have an even degree again. How do I know that? Because both sides are pointing downward, right? Down and down, where this side, you know, we got up and up, okay? What are my zeros? Hey, they're harder to see, and it's because of the scale. And I tried, actually, to copy this graph from Desmos, where it had the extra lines in it, but it just would not do right. So I apologize for not having the extra lines like the ones before do. But you know what? They don't all do that, so it's good for you. Let's take a look. I'll change my colors for you. Okay, so I have an x-intercept right here. What is that value? Now, we have to guesstimate because we don't have grid line right there. But y'all, if this is -10 out at the end, then how about this is -2, -4, -6, -8, and there's -10 right there at the edge. So that's -1 if it's halfway between 0 and -2. So let's say x equals -1 is an x-intercept, and then there's one right there. Now look, same scale, so that's x equals 2. And then there's one right there, right in the middle, and that's x equals 3. Now again, I know that's a challenge to see, but it's also healthy for you. Look, it looks like 10. You can't tell where it is because the line is right there. So even degree with those particular zeros. And then the last graph we have down here at the end, let me change colors once again. Okay, so first of all, this is an even degree too, isn't it? All of these on this page are even. Why do I know that? Because the ends are pointing in the same direction. So these are both down, these are both down, these are both up. All of those are even degrees. Now, how about my x-intercepts? I could also call them zeros. I'm highlighting them now, but where are they? Well, if that's -10 right there, and you could count 1, 2, 3, 4, and it even says -5. I just drew over the top of it. So x equals -5 is a 0. Here, x equals -2 is a 0. X equals -1 is a 0. And x equals 3 is a 0. All right, now let's go match, okay? So we have an even degree, and -1 and 6 are zeros. So let's look at my list here. The first one had an even degree, but we've already matched. Matter of fact, I'm only looking at 3 and 5. That one had an even degree, but that's got a bunch of x-intercepts, zeros, not just 2 of them. And that has an even degree, but that has 3 x-intercepts, not just 2 of them. You know what? That guy's my not matcher. So this guy right here, D, doesn't match anything. Now, E has an even degree, and negative 1, 2, and 3 are zeros. Okay. Look, right there at the bottom in the orange. Negative 1, 2, and 3 with an even degree where they both point downward. So that is, I've lost track of what letter I'm on, that's E. Okay, so 5 is E. Oh, wish it would not do that. Y'all, I don't mean to do that. It's not because I'm not being careful. I select the pen, but it just doesn't click. You know, it doesn't select. Anyway, enough complaining from me. Now, the last one has to be 3, but let's just check and be sure that makes sense. So we're saying 3, the zeros are 3, negative 1, negative 2, negative 5, and both sides are pointing downward. 3, negative 1, negative 2, negative 5, and both sides are pointing downward. So I feel pretty comfortable with that. So that last number 3 that we haven't matched, that is F. And that's a lot of work, but it's good work. It's good for you. All right, another problem with a lot of work. I think we have an A, B, and C to do here. The goal is to graph, but first it asks for the degree. So this is a degree 4. Where am I getting that from? Oh, no, it's not. Where am I getting that from? How about a degree 6? Okay, when you multiply those two together, it's going to give you a degree 6. Next is the end behavior. What's happening on the left side? What's happening on the right side? I always say up and down, but the homework says falling and rising, and we can do that. Now remember, when you have an even degree, both sides point in the same direction. We have a positive leading coefficient. Notice there's no negatives going on here at all. There's a 1 here and a 1 here. Inside or outside, doesn't matter. I'm looking at 1s all the way across there. And that means it's a positive leading coefficient, which means the left is up or rising, and the right is also up or rising. Because whenever you have an even degree, then the left and the right are doing the same thing. Positive leading coefficient, because of those positive ones, they're both up. Had that been a negative 1 out front, or a negative 2, or a negative anything else, they would both be going down. Okay, the zeros and x-intercepts are the same thing. How do you find them? You set your entire function equal to 0. So here I am, x squared minus 4 times x to the 4th minus 1. I've got to solve this. Now, it's factored, right? Well, yeah, but it's not completely factored. That's the thing. Anytime you still have exponents, then it's possible that you could factor further. X squared minus 4 factors into x plus 2 times x minus 2, because that's a difference of squares. X to the 4th minus 1, also a difference of squares, factors into x squared plus 1 times x squared minus 1. And you think we ought to be done, but we're still not. You know why? Because we still have squares going on here, which means there's the potential for more factoring. X squared plus 1 does not factor any further because it is a sum of squares and those don't factor. But x squared minus 1 factors into x plus 1 times x minus 1. Now what do? You set each one of these factors equal to 0. Now I know if I set x plus 2 equal to 0, I get negative 2. If I set x minus 2 equal to 0, I get positive 2. If I set x squared plus 1 equal to 0, I got work to do. I can subtract the 1 to the other side and use the square root property. And I get x is equal to plus or minus the square root of negative 1, y'all, is I. So that's 2 more zeros, but they're not x-intercepts. Okay? X equals negative 1 from here, and x equals positive 1 from here. Now, how many zeros are we supposed to have? Let me highlight them, because these are the zeros. Negative 2, 2, plus or minus I, negative 1, and 1. How many zeros is that? Well, that's 1, 2, 3, 4, 5, 6. Notice the degree, 6. We found them all. Okay, good deal. The x-intercepts, okay, x-intercepts are the same as zeros, Yet these imaginary guys down here, I'm going to highlight them in a different color. How about some crazy pink? Oh, no, no, no. That didn't do what I want. Okay. Let's go super light. There we go. Slightly different color. That just didn't even work out at all. Those are zeros, but they're not also X-intercepts. So if I were to list X-intercepts, just right here, X-intercepts, they're going to be -2, 0. What's up with the 0? I just wrote it in point form. 2, 0 from here. These guys don't count. They're zeros, they're not X-intercepts. Next one, -1, 0, and 1, 0. I have 4 X-intercepts. What about the multiplicity? I don't see any repeats, right? It's just 4 of them, no repeats. So they all have multiplicity equal to 1, which means on the graph, it's going to cross through the x-axis on all of those spots. Okay? Now, I'm supposed to find a y-intercept. Let me go ahead and squeeze that in on this page as well. So the y-intercept, way up here in orange, top right, you plug in 0 for x. So I can say p of x, or I could say y equals, and that's going to be 0 squared minus 4 times 0 to the 4th minus 1. You could also plug it in this factored stuff. That was just more work. So 0 squared minus 4 is -4. 0 to the 4th, which doesn't look like that at all, right? It looks like I'm multiplying by some big 4. There we go. 0 to the 4th minus 1 is -1. That -4 times -1 is +4, so the y-intercept is 0, 4. Now, it's just to plot extra points in the graph. Okay, so I'm going to transfer all of this information to an xy axis, and we'll go from there. Here we go. Okay, now, I've got all the points, -2, -1, 1 and 2 plotted, and my y-intercept up here at 0, 4. Now, if you were to match, if you were going to do matching, you could use this and the fact that both ends are pointing upward, and you're more than likely to find your matched graph. If you were to do this by hand, and I said, okay, I want you to plot points and graph, which is what I asked you to do here, it is time for a t-table. And if you would like, you could put these points on there. You're supposed to plot points between and beyond every x-intercept. So I need something out here. For instance, -3 is a good idea. This one's no fun, but I need something between -1 and -2. So -1.5. Nothing wrong with decimals. I need something between -1 and +1. But you know what? We already have that. 0, 4. So I'm just going to let that be my point. I need something between 1 and 2. How about +1.5? And then something on the other side of 2. How about 3? Now, this graph actually has symmetry, but we talked about this as a class. That's something you can calculate. The majority of graphs don't have symmetry, so I tend to not put it in my steps, but you'll see it in the homework, and I think it's a good idea, but sometimes, ooh, it's just a lot of work, right? Now, I'm going to type this in my calculator. -3 squared is 9. Actually, I'm going to do it in my head. That's 9 minus 4 is 5. -3 to the 4th. That's the one that I want to do in my calculator. But it's 81. And 81 minus 1 is 80. And then 5 minus 80 is 400. Now, you might look at my scale over here and go, that's not going to work, right? And I tried to decide how I was going to do this. But look, I got to get rid of my 0, 4. That's just not going to cut it. We're going to change this scale in a minute, and we'll put 0, 4 where it belongs, okay? So here I'm going to plug in -1.5. Remember, I got to square it, subtract 4, and then -1.5, I got to fourth it, and -1. And this isn't the easiest problem in the world to do, but y'all, you know how to plug stuff in your calculator. So you know what I'm going to do? I'm going to pause the video, plug all this stuff in my calculator, and come back, and we'll plot these points. All right, y'all, so -3, 400, we did that one together. -1.5, -7.1 was the y value. I rounded that. 1.5, -7.1, I rounded that. And then +3, 400. So again, my scale is not going to cut it. Matter of fact, you know, 400 is what I've got. Let's make this, if you want to, instead of 5, let's make it 200. Can you do that? Sure. 200, and let's make that way at the top 400, okay? All right, so at -3, I got 400. So here was -3, 400 was right there. at negative 1.5, I got negative 7.1. Now, since, you know, this is negative 200, then halfway is negative 100. Negative 7 is going to be teeny tiny. It's going to look like it's sitting right on top of the axis, but I'm going to make it a little bit lower. Remember, our y-intercept was 0, 4. I had it at 4, but I erased it because I just changed my scale. It's going to be super low also. And then positive 1.5 is negative 7.1. And then over here at 3, I got 400 again, right at the top. So what happens is the graph dips down and does that. It looks like a molar, you know, one of your teeth in the back on the top. So there you go. And that's roughly what it looks like. Now, depending on the scale you pick for your y-axis, these might dip down further or even less. Really, mine don't really dip down as far as it does there. But remember, in this class, we're just getting a rough sketch. We can't make it perfect until we take calculus because we have no way of finding what we call these minimums, these low points, relative minimums in this one over here. We don't have the skills yet to find it. There's just a whole lot you got to learn about limits before you're able to calculate those values. And so, you know, we're just doing the best we can by plotting points. Let's try another one. Oh, by the way, before I skip, look how both ends are pointing upward, and that's what we decided back over here. This is, remember, all of our information. The left was rising, the right was rising. We could have up to 5 turning points and up to 6 x-intercepts, but notice we actually only have 4 x-intercepts, and we have 1, 2, 3 turning points. We have 2 minimums and 1 maximum. So we can have up to those values, but not exactly necessarily that we have exactly those values. Now let's try another problem. Okay, we're going to answer all these same questions about this guy right here. And we have x squared minus 5x plus 6 times x squared minus 5x plus 7. Interesting. Now, what is the degree of this thing? This is a degree 4. Where am I getting that from? Well, it's not multiplied out, right? If I were to multiply this out, this x squared times this x squared is going to give me an x to the 4th, plus or minus some other stuff. But we don't care about that other stuff as far as finding the degree. We just care about that. Now, whenever you have an even degree, both ends are pointing in the same direction. I'm multiplying by a positive 1 times a positive 1 again, right? So you have a positive leading coefficient, which means the left side is pointing upward and the right side is pointing upward. Very similar to the last one, actually. Now, the zeros, remember you set the entire thing equal to 0. So that's what I'm going to do. Now, that's going to be x, I'm just recopying for the moment, x squared minus 5x plus 6 times x squared minus 5x plus 7. But now I need to factor each of these. If they'll factor, you know what? If they don't factor, to find the zeros or the x-intercepts, I'm going to have to use the quadratic formula. But look, this factors into x minus 3 times x minus 2. Those are values that multiply to be positive 6 and add to be negative 5. How about the second set? Oh, look, multiplies to be 7, adds to be negative 5. That's not happening. You know what? I can't do that. I'm going to have to use the quadratic formula. No fun, and probably exactly why I put this on the review. So, what do I know so far? I have a 0 of x equals 3 and x equals 2. But unfortunately, x squared minus 5x plus 7 does not factor. So that means we don't have zeros? No, it means we have to use a quadratic formula. So here we go. X is equal to negative of a negative 5 plus or minus the square root of negative 5 squared minus 4 times a is 1 times c is 7. And that's all divided by 2 times a is 1. Can I simplify this? See if it'll fit on the page. That's 5 plus or minus the square root of, that's 25. Negative 5 times negative 5 is 25. 4 times 7 is 28 over 2. You know what this means? We have imaginary zeros. Remember, we got a negative 3 under here. So does that mean we stop? Well, no, because it asks for zeros. If it asks for x-intercepts, we could stop because those can't be x-intercepts, but they are zeros, so I'm going to keep going. It's 5 plus or minus I square root of 3 over 2. If I write them separately, that would be x is equal to 5 minus I square root of 3 over 2, and x is equal to 5 plus I square root of 3 over 2. And these guys right here are all 4 of my zeros. How many zeros am I supposed to have? 4, right? Because it's a degree 4. Now, what about the x-intercepts? I'm going to start working on the left side of the page here. X-intercepts are the same as zeros, except for one thing, right? They're real numbers. So those ugly zeros we just found using the quadratic formula, the orange ones, are not x-intercepts. The only x-intercepts we have are 3, 0 and 2, 0. What about y-intercepts? Y-intercepts are always the easy guys to find, right? So let's easy peasy this and plug 0 in back in our the top. So it's y equals, instead of writing p of x equals, I'm just going to write y equals, and that's 0 squared minus 5 times 0 plus 6, which happens just to be 6, and then 0 squared minus 5 times 0 plus 7, which is just 7. So y is equal to 6 from the first polynomial and 7 from the second. And this is a trinomial and a trinomial. So y is 42. So 0, 42 is my y-intercept. Now again, I'm going to transfer all this information over to another slide that has a graph on it. We're probably going to have to change the scale on the y-axis again. Now, when I test you this way, I will keep this in mind. I don't want you to have to change your scale, but if you ever feel like you need to, you go right ahead. So I've transferred our information from the problem on the previous slide. Remember, we have a y-intercept of 0, 42. Plotted our x-intercept of 2 and an x-intercept of 3. So now it's time to do a t-table. We've got to figure out some good points to plug in. Now, one problem I've got, I know you see that my 0, 42 point, I can't put over here because, again, I gave you a scale from negative 10 to 10 on the x's, which works fine. But negative 10 to 10 on the y's is not working so good. Now, I don't even want to change that yet because I don't know what kind of y values I'm going to get when I plug in points. Now, remember what we're supposed to plug in. We're supposed to plug in something on the left of my first x-intercept, which is at 2. Something on the left would be 0. Well, I've already plugged in 0, 42. You can plug in another point if you want, but I think 0, 42 is good. I'm just going to recopy it here to remind us we need to plot that point. I have to plug in something between 2 and 3. Now, you think there's nothing between 2 and 3. Well, there's a whole bunch of stuff between 2 and 3. Like, how about 2.5? You have a calculator, so that's not going to be a problem at all. And then something on the other side of 3, like 4 or even 5 might be good. Now, look, I'm going to do a cute little trick. I'm hoping that maybe there's a little bit of symmetry going on in this graph. And remember, I plugged in 0, I got 42. So if I go 2 away on this side, I wonder if I plug in 5, I might get 42 also. It just depends on the shape of the graph, but it's worth a try. Now, when I plug in 2.5, I got a lot to plug in, right? I've got to do 2.5 squared minus 5 times 2.5 plus 6, and then another set of parentheses times 2.5 squared again, minus 5 times 2.5, I'm going in my graph here, plus 7. I need that space. So I'm going to type this in my calculator just like this. Now, the first time I tried typing that in, I got the wrong answer. Matter of fact, I'm redoing this video because I graphed it with the wrong answer and everything. And when I went back to check myself, I was like, uh-oh. So I'm going to type it in and tell you what I get. Stand by. Okay, so I got this tiny decimal, negative 0.1875. Or 1,875 10 thousandths, 10 thousandths. You could round that. The best I can plot, I can't even plot as good as negative 0.2, but it's tiny, 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 close to 0. Then we plug in 5, and again, remember what we're doing. We're going to do 5 squared minus 5 times 5 plus 6, close out the parentheses, 5 squared minus 5 times 5 plus 7. Okay, now this actually I can do in my head because, you know, 5 squared is 25, and that's also 25. And subtracting, and they're gone. 5 squared is 25, 5 times 5 is 25, we're subtracting, and they're gone. So really, this is just 6 times 7, which is 42. But don't hesitate to plug that in your calculator. Don't feel like you need to be doing this stuff by hand when you're just number crunching, okay? So look at my y values. I have 42 and a really tiny number. So I don't want to make this huge. You know, what if I made at the very top here, what if we change that to, instead of being 10, let's make it 50. So that's 5, 10, 15, 20, that's 25, 30, 35, 40, 45, 50. That works. And then this would be negative 25 and negative 50. And now let's plot our points. So 0, 42. So again, 25, 30, 35, 40, 42 would be right there. And then 2.5, halfway between 2 and 3, we got negative 0. So that's, oh my goodness, teeny tiny, teeny tiny. I'm still making it lower than it actually is. Because, oh, and it disappeared. What up with that? Okay, there we go. And then 542. So 5 right here. I'm up at 42 again. And this is a shape very similar to a parabola. It's not a parabola, but you will have x to the 4 graphs that are shaped very similar to a parabola. It's a little squattier down here at the bottom, even though mine is not expressing that. If you looked at the digital version of this, you would get something that looks a little bit squattier. So again, plotting points, I really want you to be comfortable with finding degree, end behavior, zeros, which ones of those zeros are x-intercepts, and what is the multiplicity of each of those. Here the multiplicity was 1 for all of the x-intercepts. Y-intercept, and then plot extra points. And you can always get a rough estimate of what the graph would look like. We can't do it perfectly yet because you need to take calculus to get an exact graph and to find maximums and minimums, but we can come really, really close. Okay, one more of these really big problems for 2.3. Let's find the degree first. Remember, that's x to the first. This is x squared. That's x squared. So the degree, when it's factored like this, you add those exponents together. So 1 plus 2 plus 2 is it's a degree 5. Now, what does that mean? Well, that means both sides are pointing in opposite directions. The leading coefficient, right here, you really would multiply the leading coefficient in front times this 1x times this 1x squared times this 1x squared. But the leading coefficient is definitely 1. Let me write that down. Sometimes I just say it and I don't make it clear. Positive, that looks 1-ish. There we go. How about a 1? And it's positive. That's what it's important. Which means the left side is falling. Very, very much like x to the third. And the right side is rising. And that's what I mean by end behavior. The zeros, we're supposed to set the entire function equal to 0. So x plus 5 times x squared plus 9, which doesn't factor, by the way, times x squared minus 16 does. I'm going to go ahead and factor it. X plus 4 times x minus 4. And to find zeros, once it's factored, x squared plus 9 doesn't factor any further, you set each factor equal to 0. So this one gives me negative 5. X squared plus 9, we got to work on that. X squared plus 9 equals 0. I got to subtract the 9. X squared equals negative 9. Then I take the square root of both sides and I get plus or minus the square root of negative 9. Right? But then that's x plus or minus 3i. Okay? And then x plus 4 equals 0 gives you negative 4. And x plus minus 4 equals 0 gives you positive 4. So those are all of my zeros. Is that all my zeros? Let's count. That's 1, 2, 3, 4, 5. Look, it's a degree 5. Sure enough, that's all my zeros. So zeros I'm going to highlight. Negative 5, plus or minus 3i, negative 4, and 4. But what about x-intercepts? Well, these dudes right here, they can't be x-intercepts. So when you talk about x-intercepts, it's only the real numbers, no imaginary stuff. So negative 5, 0 is an x-intercept. These guys aren't. Negative 4, 0 is an x-intercept, and positive 4, 0 is an x-intercept. Notice there's no multiplicity on here. None of these showed up more than one time. I probably should pick another problem that has multiplicity, but we addressed that in reverse when we did our matching. All right, what about y-intercepts? Let's do those in green or blue. Okay, here we go. Y-intercepts. How do you find y-intercepts? That's the easiest guy to find, right? You set p of x, we're going to call that y, because it is, equals. Now you plug in 0 for everything. So 0 plus 5 times 0 squared plus 9 times 0 squared minus 16, which is essentially 5 times 9 times negative 16. Sometimes they're big, especially in this section. And I got negative 720. And point form, that's going to be 0, negative 720. There we go. So this information right here, and keeping in mind that the left is falling and the right is rising, I want to transfer that to a graph, and then we'll talk about what would be good points to plug in. Okay, so once again, I got a scale issue. Notice I did put -5, -4, and 4 in blue. Those are my X-Intercepts. They're all going to cross through the X-axis because there is no multiplicity, or it's all multiplicity 1. Odd multiplicity crosses through, even multiplicity touches and goes back the other way. 0, negative 720, I got a scale issue. I don't know what I want this Y scale to be. The X scale is fine. The Y scale is not going to work out. So I need to figure out what to plug in. Now, it's a lot. We need to plug in something to the left. For instance, -6 would be a good idea. Something between -4 and -5. I never like doing that, but -4.5 will work. Something between -4 and 4. Hey, that's 0, negative 720. That might be enough, and if you wanted to plot others, you could. And then something on the other side. How about 5? Okay, now I'm going to pause it. I'm going to do those calculations. Now, let me write down what I'm doing. On -6, I'm doing -6 plus 5 times -6 squared. Be careful there, y'all. Plus 9, because that's going to be a positive 36 plus 9. And then -6 squared minus 16. Let's do that one all the way through, and then the other two I'll do silently. -6 plus 5 is -1. -6 squared is positive 36 plus 9 is 45. And then -6 squared is still positive 36. We're minusing 16, that's 20. And then I'm going to do -1 times 45 is -45. -45 times 20 is -900. It's big, but it's a nice number. Okay. Now again, silently, I'm going to calculate -4.5 the same way and calculate 5. Woo! Okay. So when I plug it in -4.5, and y'all, that's the one I worry about the most because, listen, it works just like -6. Something that you really need to point out. If you're plugging this right in your calculator, these extra parentheses right here around the -6 before you square it, those are required. Because if you don't put a parentheses around the negative number and then square it, it's going to tell you it's -36, and it's not. If you don't put parentheses there, it thinks you're only squaring the 6, not the negative. Same thing happens with -4.5. And I got 62.2, and then when I plugged in 5, it got really big. Is that a problem? Nah. But it's going to make our scale all weird, right? I don't even know if I want to put 5 on my graph, right? Let's go to 1,000. So instead of saying this is 10, let's make it 1,000. Okay, and this is -1,000, which means that's 500, and that's -500. So at -6, out here I got -900. So that would be right here. Okay, and -4.5, right in between these guys, I got positive 62.2. Now remember, that's 500, so 62.2 is going to be about there. Now don't forget 0, negative 720. So 0, I got a negative. Remember that that's -500 and that's -1,000. Then -720 would be about there. Okay, and then 5 I got off the chart. 3,600 way up there. So I just know it's going to go way up there. And I connect the dots left to right always. Comes down, connects, and then it just shoots way up. Not like that. Whew. I only want to erase part of that. Won't let me do that? Hold on, let me figure out my... Look at there. Yay! I figured something out while y'all are watching. Okay, so this shoots on up quickly. Like that. Now, is it perfect? Nope. Nope, not at all, not at all. Matter of fact, my squiggly pen on this computer makes it really imperfect. And look, I even missed a point right there. It should have gone through there before I snuck back down. But it's close. It's really close. If you type this in Desmos, it would have a similar look. What I don't know is like, does it come down here and go right back up? Probably not. It probably keeps on going down and then eventually goes up. Because remember, we don't know where max and mins are. This may go way up and come back down and pick up that 62 value. So this is just a rough estimate of what this graph looks like. But we did accurately find the x-intercept, the y-intercept, the degree, the end behavior, all of that stuff. And then we did our best we could to put it on a graph and kind of see what's going on with the graph. Okay, I'm going to wrap up the video now because it's already so long-winded, and I'm going to come back for another part 2 for problems 4 to I don't know how far.